All right, so we've basically gone over all the rules for differentiation. Okay, you can technically now differentiate pretty much any problem I give you, if it's actually can be differentiated. As crazy as that sounds. Honestly, the only ones that you wouldn't be able to do would be like the hyperbolic trig functions, but those are so rare. I'm really not going to go over those. But so now, let's actually start using it. So as I said, this is the part where it's like, okay, when will I ever actually use this stuff? Those are all the word problems that you guys hate. So let's say I have a particle that moves like this. So it's moving, but it also goes backwards. So it's not always going in the same direction. And I want to know some information about it. All right, so here's the equation. So S equals, the f of t is t to the third minus 6t squared plus 9t. So that gives me the position of the particle. And if I'll switch back over in a second. So this is basically what it is. So your position is the y. So as you can see, it's moving to the right, and then it's moving back down, and then it's moving back up again. So you have that same concept of what I just showed you in the picture a second ago. All right, so how do I find velocity? Give me the derivative of it. All right, so what's my derivative? Or what's my velocity? Oh, come on. This is the easy part. What's the velocity? Good. We're going to get much harder today. So this is the easy stuff. All right, what's the velocity after 2 seconds? So you're just going to plug 2 into that, right? So what do we get? -2. Huh? You're going backwards. Right. That's why it's negative. So let's think about it this way. So if you're in your car and you're reversing, are you going a positive speed or a positive velocity or a negative velocity? You're moving away from something, right? That'd be negative. So you have to look at, so one of the questions that we're going to look at is distance. Distance is always got to be positive. So when you're looking at how far you've traveled, yes, you'd look at both directions. But when you're talking about velocity and even speed and stuff like that, you can't have the possibility of them being negative because that would be going the opposite direction from that way. So that is a possibility. And if you look at 2 seconds, so if that's 1 second, then we're going back. So we're going backwards at 2 seconds. All right, what about 4 seconds? What was it? 9? All right, and we're going positive at that direction. So if you look at the graph, we see this, right? We're going backwards, so it's negative there, and we're going up here, so it's positive. When's the particle at rest? When what's 0? Time is 0? When velocity is 0. So if velocity is 0, the particle's not moving, right? Okay, so find me when the particle's at rest. Three? Only 3?
And 1.
And 1? 3 and 1? How did we get it? Or who didn't get it and wants to figure out how we got it? This is the wonderful factoring. What was it? 3, what was it? 3t squared minus 12t. I'm going to use x because I hate using t's. So I can pull out a 3. Right? And then I'm looking for two numbers that multiply to 3 and add to -4. So x minus 3 and x minus 1. We have 2. When's the particle moving forward? So when's it moving in a positive direction? What would that be? Well, what? When the graph is increasing, so that would mean what? My velocity is positive, right? So if my velocity is positive, which doesn't necessarily mean the velocity is increasing, it could be decreasing, but it's in the positive side, right? So we know right now that the velocity is 0 at 1 and 3, right? So I want to know when it's greater than 0. So if we look at our wonderful little number line here, I know it's 0 here and here. So where would it be increasing? Okay, so do you remember how to actually do this? Yeah, just literally pick a number in each section and plug it in and see what happens. Each section should all do the same thing. That's the point of splitting it by the negatives, right? Or by the endpoints or the zeros. Huh? Yeah. So we're going to pick a number on this side over here. It's less than 1. Let's do 0. We'll do 2 and we'll do 4. Well, we already did 2, right? We know 2 as well. -3. And we know 4 was 9 because we did those 2 already, right? And what about 0? Huh? It does not necessarily have to be positive. So in this case, yes, it's quadratic. It should go back and forth, but it doesn't have to. If we plug in 0 to this, we get 9. All right, so that means it is increasing, or it is moving positive in the positive direction from -infinity to 1 and from 3 to infinity. or if you want to say it just regular notation, t is less than 1 and t is greater than 3. Either way, those works. All right. How would we find the distance it's traveled? If you own a car that's older than the 1970s. Okay. In around the mid 60s, they actually drastically changed something in cars. Before that point, you could actually put your car in reverse and your odometer would go backwards. They didn't have a stop in it. So the odometer literally went by direction. If your car was going backwards, it was rotating it backwards, therefore the odometer would go backwards. When they realized that people were actually running their cars in reverse, just on a roller, to roll back the odometers, they put in a stop so that the odometer would just never roll backwards, but it never went forward. Now, if you hop in your car and go backwards, your odometer will keep going up. So you can't even drive. If you drove your car in reverse, and it would still count up. For a while there, it actually wouldn't count at all. So if you drove your car in reverse, you actually could put 0 miles on your car. So, but now that we've got most of that stuff all computerized, now it's not an actual mechanical system. They don't have to worry about that situation. So how would we figure out distance? We need to look at where it changes direction, right? Where does it change direction? Huh? Well, if we're looking at this, we just did this part, right? I know it's positive. It's going to the right over here, right? It's going to the left here because its velocity is negative, correct? And then it's going to the right here. So where is it changing direction? At 1 and at 3. Okay. So if I want to find out how far it went in 5 seconds, which points do we need to know? We need to know when to change directions, and we need to know the beginning and the end, right? So I would need to know where it is at 0. So not F. Let's not use F. Let's use S. And we're looking at the position. We're not looking at velocity or anything else. We're just looking at position. So I need to know S of 0, S of 1, S of 3, and S of 5. So find me those 4 points. All right, so it's S of 0. Huh? S, not V. So we're using this one. It's 0. What's S of 1? S of 3. S of 5. All right. So we went from, so 4 minus 0 is 4. That's the first term, right? That's the first direction, right? And then we have 0 minus 4, which is the second one, which is also 4. And then we have 20 minus 0, which is 20. So how far did it go? 20. I think this was meters. What was it? Yeah, meters. All right, find my acceleration. All right, what's the acceleration? 6t minus 12. And what's the acceleration after 4 seconds? 12. Actually, meters squared per, or no, it's meters per second squared. That's what it is. All right, we're not going to graph it. All right, when's the particle speeding up and when's it slowing down? Find the zeros of what? Right, of my acceleration. So it's 6t minus 12 equals 0. So t equals 2. Now we need to figure out which side's which. Right? Because we want to know when it's speeding up and when it's slowing down. So we want to know when it's positive and when it's negative. So if we make it split it 2, so if we plug in 0 and 4, plug in 0, what do we get? Negative 12. So that means it's slowing down on that side. It's negative. And we just plugged in 4 and we got 12, right? And that means it's speeding up on this side. So if we're doing from 0, so t is less than 2, it's slowing down. And t is greater than 2, it's speeding up. All right, so there's a whole bunch of stuff about high tides and low tides. The lowest tide at this place in Canada is 2 meters. The high tide is about 12 meters. So for those of us who deal within standard measurements, about 6 feet to about 36 feet. It's a rather large change in water height. So this is the function that models the water depth as a function of time and hours after midnight. So the question is how fast is the tide rising or falling, or falling at the following times? So what do I need to find first? Well, that's giving me my actual, like the height of that's giving me the depth of the water, right? But I want to know how fast the tide's rising or falling. So what do I need to look for before we actually start doing the actual calculations? Yeah. Okay, but if I plugged it into that, is that going to give me how fast it's changing, or is that just going to give me the depth of the water? Right, but I want to know how fast it's changing. We need the derivative, right? Find me my derivative. Almost everything we're going to be doing, you're going to have to find a derivative. Almost. I think I put a problem in here that you don't have to do that, just to throw you off. Hold on, I'm trying to find the. Which route is this? 24. So how do we find the derivative of this? Have to do the chain. Let's go through and do this. So I would distribute this so I don't have to deal with multiplication or anything else like that. Times 6.3.39525. So the 7 becomes nothing. That's gone. All right. So I'm going to take the 5, bring it out in front, times by the derivative of the inside, which is 0.503. Correct? Times, what's the derivative of cosine? Sine 0.503 t minus 6.75. So negative 2.65 sine so there's my derivative. Oh, that's not right. I missed a 0. That's wrong. I missed the 0 between the 5 and the 3. All right, so there's my derivative. Oh, they gave you easy ones. We'll change that one. Anybody here in the Navy? No? Okay. We get a lot of them, the rivers, and so it's like at this point, this would be easy. Switching to military time. All right, so what am I plugging in for 3 a.m.? 3. What am I plugging in for 6 a.m.? What am I plugging in for noon? 12. What am I plugging in for 9 p.m.? 21. All right, find my heights, or how fast they are rising or falling. What's it doing at 3? Rising or falling? Rising. It should be right around 2.39 or something right around that. What's it doing at 6? Rising or falling? Huh? How can it technically be rising but falling? Okay, so it's still rising. It's just not rising as quickly. So this is actually why we go through and do problems like this. Is it really starts to get to the understanding of what a derivative really is. Okay, so at 3 o'clock, it was rising at right around 2.39 meters per hour. So it was rising rather quickly. At 6 a.m., it's now rising at 0.93 meters per hour. But it's still increasing, like the height of it's still increasing. So it's just increasing at a slower rate because it's getting to that peak where it's going to start falling. Okay, so the derivative, if the derivative is positive, the value is still increasing. It just might not be increasing as fast. Okay, so it's not falling or going down until the velocity, or in this case, the derivative, is negative in that rate. So at noon, it's falling at around negative 1.21 meters. And I didn't do 9 p.m. because I changed the problem. What's 9 p.m.? My guess is it's rising around 9 p.m. But I have to do the calculation. Yep. So it's falling around negative 1.95, around there, 1.9457. So it is decreasing. So if we look at the graph of that, that's the time. That's how fast it's either changing, or that is the derivative. So that is how much it's actually changing by over time. Huh? Where was it? 3 was 2.39. 6 a.m. was 0.93. What was the one? Hold on a second. I forgot what was 21. 1.94, 1.95 for 21, or for 9 o'clock p.m. And then noon was negative 1.21. Yeah, you could, or just throw it in Desmos and type the number in. So actually what I just did here, I had that. I could have actually easily done this. And then this, I could have actually done this, and I didn't even think about it, but you just said that. 3, 6, 12, and 21. There's your 4 answers. So yes, use Desmos to your advantage. If you're producing a product, there's a lot of costs that go into it. And sometimes producing one more item might end up costing you a lot more than not producing that item. That can happen. So it's not always a nice curve where it's like, okay, it's like once I produce past this, I've covered it. It's going to be just a nice exponential curve down. It's not that way. So, and this problem they gave me, they said the cost for a company to produce a new pair of jeans, a new line of jeans is this. So 2000 plus 3x plus 0.01x squared plus 0.0002x to the third. Find the marginal cost function. Okay, we'll make this one simple. What do you think that is? That's the derivative. Good. So marginal, this means how much more the next pair of jeans is going to cost you. Okay, so that will tell me how much I'm going to have to pay to produce one more pair of jeans at that value. All right, so find my derivative. So that's what you should have gotten for your derivative. So what does the derivative tell me in general? So it's telling me the slope, right? Remember, derivatives are basically a slope. So if I was looking for the slope between a pair of 100 genes and a pair of 101 genes, that would tell me the slope between those 2 points, right? So if the derivative is going to give me the exact same thing, it's just going to allow me to do it a lot quicker than having to do those 2 points. So if we look at this one, we plug in 100. What do we get? Yeah, right around $11, right? So exactly $11 actually. So you get $11. So let's actually do the slope to verify that this actually works. How much does the 100th pair of jeans cost me, and how much does the 101st pair of jeans cost me? If I was going to make 100 pair of jeans, how much it would have cost me? That's basically what you're trying to figure out. So how much does the 100th pair of jeans cost? You're plugging it into the C, not the derivative. What was it? 2,600? And how much does the 101 pairs of jeans cost? There's a little sense after it. What's the sense? It wasn't exactly 2611. Okay. There was a reason I knew it wasn't exactly 11. Yeah. So, because I was like, I knew these two numbers were not exactly the same. But it's very close. Okay. So that's basically why we can use the derivative instead of doing out all these calculations. We can use the derivative, find that marginal cost to determine it. Why would they care? Yeah. So it's like, okay, if I'm going to make 100 pairs of jeans, I know it's costing me basically $11 per pair at that point. So it's like, how much, or the next one's going to cost me $11 more. So it's like, if I'm going to pay, charge $50 for it, I still have room to be able to make some more and still be able to make money. So we want to know where that value is to decide, okay, this is how much I'm going to make. Yeah.
Is the difference between 100 actual cost is more like it's $11
Because remember that when we just did there, we in essence did the slope, looking from point 100 and point 101. So that's looking at, there's a curve in there. So between 100 and 101, it's curving slightly. It's not exactly. So we're looking at it, when we're finding the derivative, we're finding instantaneous cost change at 100, which would be 11. So, but that there's a little slight curve between 100 and 101. That's where that 7 cents comes in. But it's close enough that we'll save time and money calculating things out to do it this way. Now, when you look at it, if I was $2,600 for 100 pairs of jeans, right? How much is it per jean? $26 for the 100. How much is it for 101 jeans? That's 101. Yeah, so it's a little less. So the amount, so we're going up. That's where that's not going to be the case. It's not going to keep getting less. It's going to actually start to increase. And that's the peak where they're going to say, oh, I'm not making any more than this value here. So. Oh, I didn't put it in there. I don't do that one. All right, let's do this one. All right, so I don't have an equation for this one. So we need to make an equation for it. So how would we go about doing it? What are some of the ways that you were taught to do word problems? Huh? Okay. So read it, write it out. All right, what else? Whenever you're solving word problems, here you go. Here are some great things to start doing. Anytime you're solving a word problem, read it, write some stuff down. That's fine. Draw pictures. Pictures are great. Pictures help. once you get the pictures and some of the information down, start making some notation or notation on it. What symbols are going to be assigned to each of the values? Is it speed? Is it temp? Or is it time? Is it things like that? So, and use things that make sense. Like when you're doing problems, everything does not have to be in X's and Y's. Okay? You can use things that make sense for the problem. And that actually makes it a lot of times easier because when you go back and look at the various values, you say, oh, okay, that means size, or that means volume, or that means the ground, or things like that, or that means ladder. It's like, use something that makes sense for the problem. All right. We're going to be looking at, in this one, it's called, these problems are called relative rates. So we're going to be doing a lot of derivatives. And we'll write equations. And then we are going to use the chain rule. We're actually doing some implicit differentiation. We're doing it to both sides. And then plug things back in to figure out what the answer is. So, but the first 3 or 4 is actually the most important parts. All right, so now let's go back and look at the problem. Draw me a picture. All right, I can see the pictures. I can see the drawing. Okay. Your pictures don't have to be like spectacular. You don't have to have like the ladders and everything else on there. It's like sometimes lines work. But part of it is literally making sure you put things in the right spots. Does that actually just matter? When you run a large difference, you get the problem right away. Little picture. And we know it's sliding away. So it's going this way at 4 feet per second. And we want to know when that hits 6 feet, right? Oh, sorry, actually. On the bottom of the ladder, 6 feet from the wall. So we want to know basically when that's at 6 feet. How fast it's moving. Yeah. Okay. So what do we have here? A right triangle. Okay. What do we know? What can we do with right triangles? That can help us find, the hypotenuse. Okay. Pythagorean theorem is going to help us relate the sides to the length, right? All right. So what's the Pythagorean theorem? Good. So in case of this problem, it's going to be
Y squared plus X.
okay. I'm going to do X squared first. Squared is 100. All right. What's that 4 feet in? It's 4 feet per second, right? So that feet is in my X, correct? And the second is time, right? So that right there is really dx over dt is 4. Does everybody understand where I got dx over dt?
Oh.
Yeah, that's just it's this one instead of the y. We are going to have one with y. We're going to have to find that because that's actually the question. It's like how fast is it sliding down when x is 6? But this right here is going to help us figure it. So we're not differentiating. We're differentiating the variable over time. Okay. So we have an extra variable in there that we kind of have to deal with. We can't. It's not d over dx or like we're not derivating based on that. We have the dt. So the x squared. This is where that chain rule comes into play. That's actually a function in terms of t. So what's the derivative of x squared? 2x. And we have to multiply it by dx over dt. Because it's the derivative of the x, because that x is a function in terms of t. Does that make sense or no? So imagine instead of it written like this, it was this. Squared. Y is... It's not. It's the derivative of x in terms of the t. So that's because remember the chain rule, we're taking the derivative of what's inside, right? So what's inside of x is a function in terms of t. We don't know what that function is. And actually, believe it or not, in this problem, we don't really care because they got some other information that are going to do it. We just need to know that there is a function there. So it could be written like this, and that's why we're taking that derivative of x in terms of t right there. So what do you think the derivative of the y squared is going to be? What was it? Yeah, 2y, and then it's dy over dt. Same reason we had the x. We're differentiating y based on t. What's the derivative of 100? Good. All right. Huh? We have to find out when x is 6, yes. So, well, we're looking for what? We're looking for how fast it's sliding down the wall, right? So we're in essence looking for dy dt. Correct? So let's solve it for dy dt. All right. So how can we find? We need to know those three things, right? What's x? So x is 6. We know the dx dt is 4. We need to know what y is. What's y? We can use the Pythagorean theorem, correct? So we know x is 6. We know c or a is 6. C is 10. What's got to be b? 8. It is a 3, 4, 5 triangle. But you could do it the Pythagorean theorem to find it too. So dy dt equals -6 over 8 times 4. which is -3 feet per second. So it's sliding down at -3 feet per second.
Whenever we use before, we don't use the best of the free
What do you mean the 4?
side.
The 4 feet per second? This? Which 4?
If you look from the
Oh, the problem?
Texas Street,
Yeah. This 4? Oh, that 4? Yeah. That was the XT2. That was good.
right, but we never.
We used it here. We didn't use it in this. We used it here. Now I see the laser pointer. I want to find out. Let's see. Anybody know how far a ladder is supposed to be away from the wall?
60, you know.
Right. That's what I'm saying. I'm like, somebody might know this. The minimum distance. It doesn't tell me. It's like I can't find. I know, and I'm trying to like do a quick search to find it, because then it was like I was going to ask you how long it was going to take him to hit the ground, but we needed to know exactly like how high up the ladder was to begin with, and then we could figure out how fast it's going to take to hit the ground. Before they jump really quickly. So, but yeah, it's that, and I actually would be willing to bet that this has something to do with that. They figured out that formula to figure out how fast, like to give them the opportunity to catch it wherever else. All right. Oh, let's do the wonderful car crash problem. I will give you the picture for it, so you don't have to try to draw it out. But then you're on your own. So the question is how fast are they going when they're 0.3 and 0.4 miles from the intersection? Yeah.
Would X equals velocity times time work here?
So dx over dt is the speed per miles per hour. So the derivative of x over the derivative of time is the miles per hour in this in relation to this problem. So we're looking for how fast they're coming together. So basically, how fast is that line shrinking? So if x is 0.3 and y is 0.4, what's z? 0.5. It's like in high school, they typically use the Pythagorean triples. They're really easy to figure out. So it's always nice to remember those. Why was my dx dt and dy dt negatives? And does it matter? Yeah. We're looking at how fast they're going towards the intersection. So the distance is shrinking. That's why we're using it as a negative speed. We're assuming the intersection is 0. So we're going towards that point. So it's decreasing. So dz dt, we have all this information now. So 0.3 times negative 50 plus 0.4 times negative 60 over 0.5.
What happened?
310. Oh, 39, sorry. We actually did 37, 38, 39. I've been pulling word problems from all three of them.
I found that,
How did you find it?
I actually didn't use the green here.
Okay.
I just used the equation from the last problem. Something values like that.
The problem is this, the only difference, wait, you still would have needed the 0.5. You just did x over y? You got lucky.
This is the problem. 2 times 0.4 times negative 60 plus 2 times 0.3 negative 15.
Something's wrong. Oh, you did
multiply
too.
by 2.
Okay. Which still should have had to divide it. What is it? 0.6 times negative 50. Interesting. Interesting. What? Oh, you made two mistakes that canceled each other out. Now I know why. Because in essence, when you were, what's 1 over 0.5? Right. So by multiplying it by 2, you in essence did that. But the way this formula was here, the 2's all cancel out, so the 2 disappeared. So that's why. I was like, wait, why is that? That's why. All right. One more. Let's see. 1, 2, 3, 4. All right. So let me pick a number from 1 to 4. First one I hear. Huh? 4. Okay, there's your problem. You're definitely gonna want to. Because that's what you're looking. Okay, triangle. Okay, we got the sun. Shadows on the ground. Everybody got that backwards. Well, most people. Oh, I was wrong. Never mind. I said a 400-foot building. I thought for some reason I was reading it as a 400-foot shadow. So never mind. Switching back. And the 0.025, which would be d theta over dt. Yeah, I read it as a 400-foot shadow. Now you need an equation. You are not using Pythagorean theorem. It is something to do a tangent, but you can't put the 125. Remember, the 125 is a derivative. It's d theta over dt. It's actually pi over 6 is your theta. You're gonna have to find the derivative of this one. You did not fix the one problem that was not the derivative. That was a constant. That's why I was trying to figure out what you did to get the class for it. That's come up with something. Worst case, you're wrong, and I tell you to fix it. Don't put your 5 or 10 together. Remember, you're looking for derivatives, so don't put the numbers in there yet. Find derivative first. But you need to find the equation before you can find derivative. Just change that to beta. And you have the equation. First, I would try to get rid of more. Because I don't care how long that distance is, I'm looking at the angle, how the angle is changing. So as this changes, we want to know how long that is. Most people got to here, which is fine. Or you kind of got to there, but you kind of flipped numbers into it. But I don't want division. Division's going to make your derivatives horrible to deal with. So flip it and use cotangent. Then you don't have to deal with the derivative. I mean, you don't have to deal with the division. You just have to look up in your book what the derivative of cotangent is. Go on your note card if you start writing. What's the derivative of cotangent? Yeah. And then d theta dt equals dx dt. Because remember, that's a function again. Remember, we're doing it in terms of time, not in terms of theta. If we were doing it in terms of theta, we wouldn't have cared. But all these problems basically are relating it to time. How fast is something changing over time? And we figured that we got that from that part of the problem where it said it was 0.25 radians per hour. So now we can plug in our values because that is theta. So 400 times cosecant square root of pi over 6 times 0.25 equals dx dt. And really, so I have 400 times 4. So dx dt. So the shadow is growing at 400 feet per hour. So on Thursday, I won't give you more word problems, don't worry. I'm just going to give you a whole bunch of derivative problems. And you guys get to figure out how to start them and how to finish them. That's what we'll do on Thursday. Basically be a start to the review for the test book after vacation. Yes, I know, I forgot. I will do it first thing tomorrow morning. I'll upload this one and that one. I was going to do it when I got here, but I got here late.